Imagine a tool so simple, so familiar, that almost everyone takes it for granted. A wheel. For centuries, it has been the backbone of transportation, industry and progress here on Earth. But what if I told you that in the harsh alien landscapes of the Moon and Mars, this simple invention was completely reimagined? That engineers had to reinvent it from scratch to overcome challenges humans had never faced before? Tonight, we are about to embark on a journey beyond our planet, exploring how ingenuity, science, and sheer determination turned an everyday object into a revolutionary instrument of exploration. We'll uncover the secrets behind materials that bend without breaking, designs that adapt to impossible terrain, and the extraordinary ways these innovations have shaped both space travel and life back on Earth. Stay with me as we dive into the story of how humanity transformed the wheel, pushing the boundaries of what we thought was possible, and discover the future of mobility among the stars. You won't want to miss a single moment of this fascinating journey. The first keynote, focusing on innovation driven by extreme environments, highlights how NASA's approach to wheel design was shaped by challenges far beyond those faced on Earth. Traditional wheels are engineered for stable roads, predictable weather, and standard gravity, but NASA needed wheels that could perform in environments completely alien to human experience. On the Moon, gravity is only 1/6 of Earth's, meaning that wheels had to provide traction without relying on weight in the usual way. Mars presented a different set of obstacles, including fine dust, loose sand, and rocky terrain that could easily trap or damage conventional tires. Engineers had to completely rethink the purpose of a wheel. It was no longer merely a circular object for rolling, but a complex instrument capable of adapting to unpredictable surfaces. Extreme temperatures added another layer of complexity, as materials on the Moon can swing from boiling hot to freezing cold within hours, and conventional rubber or metal would fail. NASA responded by experimenting with lightweight metals, flexible yet strong alloys, and designs that could deform under pressure without breaking. Shock absorption, grip, and stability had to be engineered at a molecular and structural level, ensuring that wheels could handle the stress of climbing craters or skimming across regolith. This environment-driven innovation led to wheels that were not just functional but revolutionary, opening the door for mobility in places where humans could not tread safely. By letting the challenges of space dictate design principles, NASA created solutions that were radically different from Earth-based thinking, setting a precedent for engineering that merges creativity with extreme practical demands. The second keynote, focusing on material engineering breakthroughs, emphasizes how NASA had to redefine what a wheel could be made of to survive and perform in extraterrestrial conditions. On Earth, wheels rely on rubber and standard metals, but these materials would fail under the extreme environments of the Moon and Mars. Temperatures in space can swing dramatically from blistering heat under direct sunlight to freezing cold in shadows, causing ordinary materials to crack, warp, or lose flexibility. Weight is another critical factor, as every kilogram sent into space requires significant fuel and cost, meaning wheels had to be lightweight, yet exceptionally strong. To meet these demands, engineers experimented with advanced alloys, memory metals, and composite structures that combined strength with flexibility. Some designs used woven metal mesh or aluminum frameworks that could flex without breaking, absorb shocks from rough terrain, and maintain traction on soft soil or rocky surfaces. These materials had to resist wear over long missions, sometimes lasting years, without the possibility of repair. In addition, material scientists incorporated innovative coatings to reduce friction, prevent dust accumulation, and protect against radiation. The result was a wheel that was lighter, tougher, and far more adaptable than any conventional tyre. This material-focused approach not only solved the immediate challenges of extraterrestrial travel, but also inspired innovations on Earth, influencing designs for military vehicles, off-road transport, and robotic systems that benefit from lightweight, durable, and flexible materials. By pioneering new materials specifically for extreme conditions, NASA fundamentally redefined the possibilities of wheel engineering, demonstrating how necessity drives innovation at the molecular and structural level. The third keynote, focusing on non-traditional wheel designs, highlights how NASA completely reimagined what a wheel could look like and how it could function in environments vastly different from Earth. Conventional rubber tires with treads are designed for paved roads or even off-road terrain on Earth, but such designs would fail on the Moon or Mars. The surfaces there are uneven, filled with loose dust, sharp rocks and craters, while the low gravity reduces traction and makes traditional rolling inefficient. To overcome these challenges, NASA experimented with entirely new wheel structures, moving away from solid or pneumatic tires toward mesh, wire, and modular frameworks. Lunar rover wheels, for example, used a flexible metal mesh, with chevron-shaped treads that could grip loose soil while deforming over obstacles without breaking. Some wheels were designed to expand or contract slightly to adapt to terrain, acting almost like shock absorbers integrated into the structure itself. Modular designs allowed parts of the wheel to move independently, distributing stress and preventing catastrophic failure if one section encountered a sharp rock or deep sand. These wheels were not only functional but also highly efficient, minimizing the energy required to traverse miles of alien terrain. NASA's exploration of non-traditional shapes and structures demonstrated that a wheel does not have to be perfectly circular, rigid, or uniform to work. It can be an adaptive system responding dynamically to its environment. This radical redesign opened the door for mobility solutions in extreme conditions, showing that innovation in form and function can solve problems that traditional engineering approaches cannot address. The fourth keynote, focusing on the integration of science and mechanics, illustrates how NASA's wheel designs were not just mechanical objects, but the result of careful calculations combining physics, material science, and engineering principles. Thus, designing wheels for extraterrestrial terrain required understanding how forces like traction, momentum, and weight distribution would behave in low-gravity environments. On the Moon, for example, a rover's weight is drastically reduced, meaning that wheels cannot rely on mass alone to maintain grip or stability. Engineers had to calculate how to distribute the vehicle's weight across the wheels to prevent slipping or tipping while climbing inclines or crossing loose soil. Similarly, angular momentum and rotational dynamics had to be optimized so that the wheels would maintain smooth movement over rocks and craters without causing jolts that could damage instruments or astronauts. Material properties also played a critical role as metals, composites, and alloys respond differently to stress, temperature changes, and repeated flexing. Shock absorption, friction, and deformation had to be predicted using simulations, ensuring that wheels could bend and flex over obstacles without permanent damage. Even the placement of treads and the overall geometry of the wheel were engineered to maximize traction and stability, often inspired by natural designs and principles of biomimicry. By combining scientific knowledge with mechanical engineering, NASA created wheels that were not only functional, but optimized for performance in alien landscapes. This interdisciplinary approach ensured that mobility in space was reliable, efficient, and capable of handling unpredictable conditions, transforming a simple wheel into a sophisticated tool for exploration and discovery. The fifth keynote, focusing on the impact on earthly technology, demonstrates how NASA's innovations in wheel design have influenced applications far beyond space exploration. The challenges of extraterrestrial mobility, low gravity, uneven terrain, extreme temperatures, and the need for lightweight yet durable materials pushed engineers to rethink traditional concepts of rolling and traction. These advancements did not remain confined to rovers on the Moon or Mars. They inspired improvements in robotics, off-road vehicles, and emergency response machines on Earth. For example, flexible metal mesh wheels and modular designs developed for lunar rovers informed all-terrain robotic systems that can traverse rubble in disaster zones or navigate uneven agricultural fields with minimal risk of getting stuck. The development of lightweight alloys and memory metals for space wheels also found applications in military vehicles, improving durability and reducing fuel consumption. Even in prosthetics and mobility aids, NASA's principles of weight optimization, flexibility, and energy-efficient movement have helped create devices that allow smoother, more adaptive motion for users. The design philosophy of integrating science, mechanics, and environmental adaptation has influenced vehicle engineering, robotic exploration, and industrial machinery, encouraging innovation in industries that require wheels to perform under extreme or unpredictable conditions. Furthermore, these Earth-based applications continue to benefit from ongoing research in wheel technology for space, as NASA experiments with self-adjusting treads, improved shock absorption, and traction systems that can handle soft soil, sand, and rock. By translating lessons learned from extraterrestrial mobility to practical solutions on Earth, NASA has not only revolutionized wheels in space, but has also reshaped how wheels are designed, tested, and applied across multiple fields. The sixth keynote, focusing on the future of mobility in space, highlights how NASA continues to push the boundaries of wheel technology to meet the demands of upcoming missions to the Moon, Mars, and beyond. Space exploration is evolving from short-term robotic missions to long-term human presence on other planets, which requires wheels that are not only durable but also adaptive, intelligent, and capable of functioning autonomously. Future wheels must navigate complex terrains such as steep craters, loose regolith, icy surfaces, and sand dunes, while carrying heavier payloads, scientific instruments, and habitats. Engineers are exploring designs that can change shape, adjust traction, and even self-repair minor damage during a mission. Advanced sensors embedded in wheels may allow real-time terrain analysis, helping vehicles adjust speed, angle, and torque to avoid getting stuck or damaged. NASA is also investigating modular and interchangeable systems, where parts of a wheel can be replaced or reconfigured in the field, reducing the need for spare equipment and ensuring longer operational life. These innovations are part of a broader approach to create mobility systems that are intelligent, energy efficient, and capable of handling environments humans have never directly experienced. The lessons learned from these advanced wheel designs will influence not only future extraterrestrial exploration, but also autonomous vehicles, planetary construction robots, and even emergency response systems on Earth. By continuously reimagining what a wheel can do and integrating technology, materials, and design, NASA is ensuring that mobility in space will evolve far beyond traditional concepts, allowing humanity to traverse and explore planets and moons with unprecedented reliability, efficiency, and adaptability. In conclusion, NASA's revolutionary approach to wheels demonstrates how necessity, creativity, and science can transform even the most familiar tools into extraordinary innovations. By tackling extreme environments, developing advanced materials, rethinking traditional designs, integrating physics and mechanics, and inspiring Earth-based technologies, NASA has redefined mobility both on our planet and beyond. The ongoing advancements promise a future where space exploration is safer, more efficient, and increasingly adaptable, opening doors to new possibilities for human and robotic presence on other worlds. This journey of innovation reminds us that challenges are opportunities to think differently, push boundaries, and create solutions that can change the world in ways we never imagined.